thanks for everyone joining. I feel a little bit like an imposter here because I'm new to Nix. I haven't used it, but I'm very much looking forward to also making use of it in the context of the talk that I'm going to present here. But still, I hope you will be entertained or learn something new today with this talk. I'm going to talk about Cashu, which is a Chaumian Ecash system for Bitcoin. In short, it is a way how we build custodial Bitcoin services that are unable to track their users and offer an excellent level of privacy. And this will be the main focus of this talk today. We've been taking this concept that was originally invented in the 80s, Chaumian Ecash, and really bringing it back, bringing it to today's world and combining it with Bitcoin and doing all sorts of crazy experiments with it that I want to show you today. So the main theme of this project is basically summarized by blinding custody. There are two main risks in using custodial systems today that all of us Bitcoiners know of. And the first one is the custodial risk, which is the ability of the custodian to run away with the money. Cashu does not address this problem. I refer to Fediment, which is an excellent Chaumian Ecash project that also builds on Bitcoin to minimize the custodial risk. However, today I want to talk about the second risk of custodial systems, which is complete transparency of the user's activity when you use a custodial system. So the problem, basically a very simple problem definition, is that a custodian, in order to provide services, needs to know all your activity, your balances, and the payments in and out of a system. And an alternative approach for a custodial system is using Chaumian Ecash instead of using classical ones. So this is the beautiful image that Nifty made for my avatar for this talk. We use custodians everywhere in our daily lives, and this poses a huge problem to our privacy, especially for smaller amounts, which we tend to be okay with using custodians. For example, you would have some Satoshis on a wallet of Satoshi or something like that because you want to benefit from the properties of having an online wallet. But since you pay your coffee with that and your magazines online and whatever you read and consume, it leaves arguably a very important or very critical trace of your activities. So some examples of custodial systems that I use or that everyone knows. Here you can see Stacker News. I'm an avid user of Stacker News. You can post about Bitcoin and earn Satoshis. You can see my balance up there, and whenever I make a post, someone can upvote my post, and I get some Satoshis for it. Obviously, I'm using Albi, which makes it very easy to interface with the Lightning Network in a browser. It's a custodial system where the service provider also knows what you're doing, which websites you're visiting probably, or at least which invoices you're paying, so the destination of these invoices as well. Wallet of Satoshi, I already mentioned it. It's a must mention because it's the largest Lightning service provider, user-facing service provider that we have today. Looking at Nostr itself, and this is also fueled. This also fuels the use of custodial systems. We can see that when you count the number of zaps that people do, above 90% of zaps are from custodial wallets or to custodial wallets, which is understandable because you want something that is online all the time, and not many people go through the hurdle of setting up a Lightning node to receive a couple of Satoshis on Nostr. Obviously, now exiting the Bitcoin world, if we go into fiat world, everything is custodial except for the cash in your pocket. So there is no way to interface fiat non-custodially. This also extends to services that we consume on the web. Here, as an example, it's a standard paywall or subscription services. You could also argue these are kind of custodial, even if they don't feel like, because you make a payment and then you expect a service in return over a course of a month, for example, which puts you in some kind of a trust relationship, although there is not so much trust in losing your money and them running away with that. Similar for streaming services where you pay these monthly fees. So all of these systems that I just showed you work in the same way. And this is how, and it's very easy to understand. If you have worked with these ledger-based systems, you already know this. We have Alice, and Carol, both are two users of the system, and we have Bob in the middle. This is the custodian. And when Alice wants to send Bitcoin now to Carol, what she says to Bob is, please, Bob, here's my ID. Here's the ID of my counterparty. Can you please move 1 BTC to Carol? And then the custodian here needs to basically check whether you both have a valid user ID, and then pops up a database in which all the past transactions are in. So you can see some couple of transactions already happened, and Alice has enough money, right? We check first, Alice has enough money, and then add 2 new entries to this ledger, just subtracting from the sender, adding to the receiver, and then we ping Carol, and Carol says, nice, I just received some Bitcoin. So all this is to simply explain that this system is built purposefully because we don't know of any, this specific system of any other way how to build it without the service provider really knowing everything about what you do. So Chaumian Ecash works completely differently, and we will start again with the same actors here. We have Alice and Carol, and Bob is now our mint, or the custodian. We call it sometimes the mint in the Chaumian Ecash context. You could think of it as a bank or whatever service provider you want. And now if Alice wants to send a 1 BTC to Carol, instead of pinging the mint directly, she pings Carol directly. And this can happen over any communication medium. It could be a chat or a QR code or whatever. And basically, Alice takes some piece of data. Now, Chaumian Ecash is represented as a piece of data on your device. It takes it from your hard disk and then sends it over this communication medium to Carol. Now, you will think, this can be double spent. This is just digital data. I can copy and paste it and send it again from Alice to Dave, for example. In order to prevent that, the transaction is not yet complete. We have to first send this node to Bob, and then Bob does the following. First of all, it checks the signature on that object on the eCache and says, yes, this is actually correctly signed, and then destroys this eCache by putting it onto a ledger. Now, this is the only database that we need to carry. It's a list of seen eCache nodes, and if the node wasn't seen yet, then it can create a new green eCache node, as you can see here, and send it back to Carol. And now the transaction is complete. So basically, we have done this dance from Alice to Carol, and then from Carol to Bob, and then back from Bob to Carol. Now, this was an eCache transaction. The properties of this eCache system that I will be explaining a little bit further along this talk is, first of all, the entire process that I just described is completely untraceable if you, excluding any network level observations. That means that the mint itself does not know who was the previous owner of this eCache when it received it, for example, when it got the pink one and reissued the green one. So it makes it untraceable. eCash is also a bearer token in its original sense, meaning that the data is not just an access to money, it is the money. So moving the data from one person to another means moving the money. And that also means that you can put the data into another communication protocol and send money over that protocol. I will give some exotic examples on that later. Different from Lightning, I've been working a lot on the Lightning space. In the Lightning system, you have a pull-based UX where you first create an invoice and then someone can pay that, except if you build something around that. eCash is different from that. You basically take eCash and throw it at the receiver, and if the receiver catches it, then the payment is almost complete, excluding the double spending path that you also need to go. And lastly, eCash is programmable. This is heavily inspired by how Bitcoin itself works. Turns out you can program money, and this enables very, very cool things, also with eCash that I will be touching on later. So, Cashu is an eCash project. How does Cashu work? There are a couple of different Lightning wallets that people have built. You can check out enuts.cash, which is a very advanced iOS and Android wallet, minibits.cash. Both of these are native apps, but there are also Nutstash and Cashu.me that are progressive web apps that you can run in your browser and install on your device, and which makes it feel like an actual app. So, There are many different implementations that people have built so far in the year of the existence of this project. I will just mention a bunch of mints that people have built. So we have the Nutshell and LN-bits integration, so you can run this Chaumian Ecash mint in your LN-bits. And also want to mention 2 Rust implementations that are also working as mints. There are many more wallets that people have built. This is because devs have come up with libraries, and libraries, turns out libraries are just the absolute amplifier of development and low time preference way of building things. And you can see that the list is arguably longer than the previous one. I also have this group called integrations, where we really want to experiment more on how to put this Chaumian Ecash system into existing apps. 2 of my favorite Nostr apps, Snort and Amethyst, both have implemented some parsing for tokens, and you can just press one button, and then it gets, if you see a Cashu token, you press one button, and it gets deducted to your Lightning wallet, for example. And I also want to mention a category maybe called new use cases or some exotic use cases, things that we can now achieve because we actually work with a bearer UX token. And so Cashu and Proxnode are 2 examples that I will be giving, and Katzenpost as well. This is to summarize basically the idea of taking the Ecash and putting it into a data package for payment of a service, something that I will be showing later as well. So just to quickly go over milestones, because so this project has been around for 1 year, and people have joined building it, and we have achieved some remarkable steps in the meantime, I would say, in the short time. First of all, it's fully integrated with Bitcoin Lightning, so you can interface the Bitcoin network using the Lightning network. We have achieved also generating the Ecash deterministically, which means that previously Ecash was known for this problem of you lose your wallet and the money is gone, or you have to make an update with every single state change in your wallet, similar to very old Bitcoin wallets. But it turns out you can also generate your Ecash deterministically, similar to how we generate Bitcoin addresses. So this has been also implemented in a few Cashu applications. We've been working around with programmable Ecash with spending conditions. Here as 2 examples, pay to public key and multisig. We are working on a proof of liability scheme. Ecash is also notoriously known for not being auditable, so anything that makes it more auditable gives more trust to the system. And since this is basically a trust-based system, it's important to be able to prove to the public or to the users of a mint that the mint has not printed Ecash out of thin air, and this is what the proof of liabilities scheme is about. So you can talk to me later if you're interested in particular. We are also working on receiver offline transactions. This also works. You can lock Ecash to a specific receiver, and if the receiver is offline, they can take the Ecash, and there will be no double spending possible because it was locked Ecash. So this is very interesting and attractive also for cases where the receiver either does not have internet, or you want to just avoid talking to the internet because you want payments that are extremely fast. Finally, we have a couple of libraries and integrations and implementations that people have built. All right, so here this is the gist of my talk. Actually, you can, if you forget everything what I say, this is what you should remember, because this is the actual lesson, is how blind signatures work. And blind signatures are a cryptographic primitive, and if you understand it once, it just clicks in your brain and feels awesome, and you can use it in your life. So a blind signature, a definition of a blind signature is very simple. So it says a blind signature allows you to sign a message that you have never seen, and to verify that your signature once the message is revealed to you. So you can think of it as someone basically, closing their eyes, making a signature on a document, never seeing the document, which would be, reckless, obviously. But once someone comes back with a document and you see the signature, then you can recognize it's your own. This is similar how blind signatures work. Another popular example that people use to explain blind signatures, a physical example that everyone can kind of imagine, is a carbon paper envelope example. So basically you have a carbon paper envelope. This is the paper where you press through and then it leaves the markings on the paper below. Imagine a carbon paper envelope, and then you take a contract and you put that contract into that carbon paper envelope. You close the envelope and send it to the bank. And then a bank takes a pen and signs the outside of this envelope without opening it up, and then sends back the signed envelope to you. and you can open the envelope because it was encryption, right? And take out the contract, and you see a signature there. So that's also a blind signature. How does it really work? So we have Alice and Bob. Alice is the user, Bob is the bank. Alice creates a secret. Now, this is the contract in my previous example. It's just a random string, random data, and then blinds it. So basically encrypts it with a secret that only she knows. So Alice encrypts that data and sends it over to Bob. Bob takes his cryptographic pen and makes a signature there and sends you back the signed envelope, basically. And then since you were the one who encrypted this message, you're the only one who can decrypt the signature. And what you get at the end is this message that Bob has never seen and a signature that Bob can verify. And this is what we do when we spend Ecash. So here you can see this icon reappear that I showed previously in a couple of slides before as representation of Ecash. This is the Ecash. So the secret that I've generated and the signature together is Ecash. This is the money. So when you spend the money, you present this tuple to Bob, and Bob can just do the signature check and say, yep, this is okay, and burn the Ecash and give you something in return. So this is blind signatures. The most important property of all this, and the reason why this is a blinded scheme, is because we want to unlink operations. And if you want to take even a more bird's eye view of this, you can think of the blind signature schemes used in Ecash systems as a way to unlink operations. So formally, you would have, in a classical ledger-based system, you would have these events, plus 1 BTC for Alice, minus 1 BTC for Carol, and so on and so forth. But these all depend on what has happened before. If you want to have these operations unlinked from each other, statistically uncorrelatable, then you can use blind signatures. And this is basically what it achieves in Ecash. But why I'm putting an emphasis on this idea is once it makes sense in your brain, then you can use the same operation to build authentication systems that are blind, to build, I don't know, some voucher system, or whatever, your supermarket might give you some customer credits or whatever you want to design, with the point being that it remains fully anonymous for the users. Okay, so we have just explained how a Chaumian Ecash system works, and you can think of it as a universe inside, and people are playing around with Ecash. But what are these Ecash tokens worth? Obviously, they're not worth anything because it doesn't cost money to print them. However, when you embed such a system into an already existing economical framework, such as the Bitcoin system, you can actually start making use of them and make real economic transactions. And this is why we implemented Cashu and integrated into the Lightning Network. So there are two main operations in Cashu interfacing with Lightning. The first one is the endpoint called /mint. Basically, this is how tokens are generated. And in order to generate an Ecash token for, let's say, 100 sats, you need to pay an invoice for 100 sats. So it says, hey, Mint, I would like to generate some Ecash. And then the Mint says, okay, pay me this Lightning invoice. Basically, you pay the Mint. And then once you make that payment, the Mint generates, you do this back and forth. You send the blinded secret to the Mint signs it, sends you back the money. So this is now you have Ecash that lives in your hard drive. The Mint has never seen that Ecash, and you can later spend it. And when you want to later spend it, again, you want to now take your Ecash and pay someone on Lightning. You basically do the reverse. You say, hey, can you please pay this invoice for me, dear Mint? And then the Mint says, okay, I have a Lightning node. I pay this invoice for you if you give me Ecash for it. So this is how we can generate Ecash and destroy Ecash. I should mention also, this looks a bit artificial, this relationship between Alice and Bob, but when you open a Cashu app that feels like a Lightning wallet, this is what's happening in the background. So you can imagine a user doesn't even need to see anything about the Ecash happening. It's just they only see the Lightning stuff. So it feels exactly like Wallet of Satoshi, but in the background, there is no user accounts or anything. It's just this sending around and signing and unblinding Ecash and so on.
But it is not that terribly different from the United States normal money at this point. Somebody works for
Yes, but it's blinded, yeah. I mean, your bank account could use Ecash as well, but the
But the $5 bill that is allegedly played to me, it has a serial number on it, but nobody is going to look at that serial number. It is effectively most people considered a $5 bill sitting in their pocket to be anonymized because nobody is looking at serial number 227650 in Pennsylvania Mint or
yeah,
whatever.
you're right. So Ecash has similar properties to physical cash. So it's basically similar properties, I would say. Yeah, that's true. Okay, so we've talked about Lightning and how it works in the context of a single mint, right? And you can think of this one mint now with a couple of users here. And we've also seen how users can send each other Ecash. So when users want to communicate with users, they can use whatever protocol they want. They could do it over Nostr, QR codes, Telegram, whatever. We've also seen how a mint communicates with the external world, which is over Lightning. Now, you can think of obviously, so Cashu is not built, we don't want a monolith that just a big bank that runs the entire system, but the idea is making everyone be able to run the system very, very easily. So, and that's also where Nix comes in. So you can think of a second mint with their own users in their own application or some website that offers something and they have their own users. But some users might have accounts in multiple mints, as you can see. Or no, I shouldn't say accounts, but Ecash. Have Ecash from multiple mints. If you don't have that and you would like to, you're a user at this green mint and you want to pay a user at the pink mint, the only thing that you can do is to go over Lightning. And this is how basically the mints communicate between each other. They use Lightning as a settlement layer in between. And I've lent, I think, this expression, Lightning, the connecting tissue in this Cashu ecosystem from Nifty 9. All right, so let's get into more advanced stuff. Programmable Ecash. So the most basic spending condition for Ecash is you cannot spend me twice, right? That's so basic that you don't mention it. But we can attach more complex spending conditions to Ecash. You can think of it very similar to Bitcoin UTXOs, where you attach a lock to a UTXO and only someone who can unlock that lock can spend it again. You can similarly attach a lock to Ecash. One example that I will be giving is pay to public key. So pay to public key in Cashu works the following. First of all, Carol, the receiving user, needs to generate a public key and a private key that she keeps secret, but the public key she can share with the world. That is something like a Bitcoin address. And the Bitcoin address, or this public key now, this Ecash address, is represented as this green lock. So you send the green lock to someone else who would want to send you money. This is QR code, for example. And then Alice can take her Ecash that she takes from her wallet. This is ordinary pink Ecash, and attaches this lock to that Ecash. She does that by destroying the pink one once and then getting back one that has a lock attached. Interestingly, the mint doesn't know that this happened because everything is blinded. Then Carol takes the locked Ecash and sends it, Alice takes the locked Ecash and sends it to Carol, and Carol still needs to, take out the lock in order to do whatever she wants with it. And for that, she sends it once to Bob. And now Bob says, okay, this is special Ecash. It has a lock attached to it. I want a signature for you to spend it. And Carol needs to provide the signature. Here you can see an equivalent of a simple Bitcoin script. We even implemented Bitcoin script, but it doesn't matter. It's just some lock and a witness, and that's it. If you can provide the witness, I can take off the lock, basically, and you can spend the Ecash, and in return, I give you a green one. Now the transaction is complete again. So this is interesting because with this, you can do a couple of things that were not possible with the naive scheme. First of all, you can post this Ecash publicly, right? Previously, whoever finds the Ecash can spend the Ecash. Anyone can spend. Now you can attach a lock to the Ecash, which means you could post it publicly, for example, on Nostr, and everyone could see that someone has paid someone else, but only the receiver can actually spend the money. What I found even more intriguing is the receiver can remain offline. So again, just to reiterate, if you're offline, I know your address, I can attach a lock to Ecash, and while you're offline, I can just post it somewhere. You, as a receiver, only need to see the Ecash, and you know it cannot be double spent. You don't even have to go back to the mint and take off the lock and get a green one or whatever. You can defer that into the future as much as you like, because if you see the Ecash that has your lock attached to it and the signature of the mint is valid, the transaction is complete. And this enables some crazy fast payments, and something that I also have a slide of later. Oh yeah, so this is just what I explained. By pre-locking Ecash to receiver, you can basically send money as fast as the data travels in the network. One other thing that we've been working on and implemented are hash time lock contracts, HTLCs, which is a primitive that we use on Lightning. And basically, the idea is either you unlock Ecash using pre-image of a hash, or you wait long enough so that the sender can redeem it back. That's the time lock. And with HTLCs in Ecash, you can do almost all the things that you can also do with Lightning, and you can do it with Lightning together. So you can have atomic swaps of Ecash with Ecash to Ecash, or you can have an atomic swap with Lightning to Ecash and Ecash to Lightning. So we could be two Cashu users, and you don't have a Lightning node, I have a Lightning node. I could offer you to make a Lightning payment for you if you give me Ecash in return, and this happens atomically, so no one can rock anyone else, if both of us trust the mint, right? So this is a way to get rid of the trust two users need to have towards each other by delegating our trust to the mint. Some very exotic ideas that has been not worked on, but I just want to mention it as food for thought, is that this, in a situation where you can handle HTLCs with Ecash, some people were even theorizing about taking shortcuts on the Lightning network. You can think of routing an HTLC on Lightning and going over a shortcut, through a Ecash system. If the sender knows the path that is possible, I could take Ecash and forward it to the other Ecash user, then continues back on the Lightning network. Everyone would still have the agreed upon trust relationships they have. Most of the Lightning users don't need any trust, but those in the middle can, if they trust the mint, they can create these shortcuts in the Lightning network. So this is also one way to improve the connectivity inside the Lightning network. All right, so at the end, I want to mention a couple of advancements that we have done with this simple protocol that we called Cashu. This is an attribution to the headers in the HTTP protocol that you can add to your requests. Basically, what we're trying to do, like a couple of other projects as well, is to unearth the lost and forgotten error code, HTTP 402, payment required. And I really think this one vibes really well with Ecash because of its UX bearer token nature. So you can think of a client and a server. Server offers some service. Client says, hey, get API. And then the server says, no, I want money for that request. Give me some Ecash in return. Now what the client does is take some Ecash inside the GET request of the HTTP, of the HTTP request, put the Ecash into the header. And this Cashu project that we've built is basically a collection of reverse proxies or middlewares that can be put between the client and the server. And this reverse proxy just takes out the Ecash from the HTTP header, checks whether it's valid, yes or no, and then the server replies with their service. Most importantly, the server here does not need a list of users, does not need to track their accounts, does not even know which user corresponds to which request, and also doesn't know that two requests from the same user came from the same user, except if the user uses a unique IP or other network-related tracking. That was me. So here's an example of what one of the Cashu devs has built. This is called Proxnut. You can find it on proxnut.com, which is a paywall that was implemented with this idea. So this is almost perfectly anonymous paywalls that you can build that work with Lightning. So this is a website, it's a demo site. You can see 3 buttons. All of them, they cost money to press the buttons. You want to get content behind the button. And here on the upper right, you see very small, it's a Cashu wallet. It's a little bit of JavaScript that you can import into your front end, and then it's just a Cashu wallet that lives there. So you can see me trying to press the buttons, and then the server says no. And I need some nuts. So I click on the Cashu wallet here, and you see it's 0 nuts. Press top up. This creates a Lightning invoice that I now take my phone and scan this with my Lightning wallet. And a couple seconds later, I have now 20 Satoshis in that wallet. And as you can see, once I press these buttons that cost money, it deducts Ecash from my wallet that you see up there, pays the server responds with the content. Yeah, better don't ask why. All right, to conclude, this is my last slide. I'm sorry for being already half a minute too late, but to conclude my presentation, I want to give one more application that we're working on, also thinking about how we can implement this in other solutions. I call it here onion routed Ecash because it really blows my mind. So you know, all of us know Tor. Some of you also might know Katzenpost or mixnets in general. Basically, you can think of it like Tor on steroids. One problem with these services is that they would like to, often these services would like to have some kind of a payment system inside to incentivize people hosting these nodes and so on. But which payment system is, first, private enough, and second, fast enough to allow for that? And there's almost nothing that I can think of, especially blockchain-based currencies. So the idea is, as in the previous slides, put the Ecash payment inside the request itself, but the idea squared here is the package itself is an onion, so we can put multiple payments inside one single package. So you have this situation. The client is on the left, and the server is here on the right, and there are multiple onion routers in the middle. So what the client does is generates an onion. This is the package, the data package that you will be sending around in the network, and then put some money into each layer of the onion. So, you know, the next one opens up the onion, sees some money, takes out the money, okay, and then sends it further to the next one. Opens the onion, sees some money, okay, and sends it to the next one until the actual data receives the recipient. So these are some of the things that we are working on. If you are interested, you can join our Ecash Hack Day. This is a satellite event to this conference, ecashhackday.github.io. It's on Sunday. Please register if you want to come. And thank you for your attention. May the nut be with you. And encrypt your backups.
Cool. Well, we have time for one question.
One question.
For minting, is that currently not atomic? So when I do the mint, so I do the Lightning payment and then I receive the Ecash back, that's currently not atomic in the protocol.
Yes. So currently the minting process relies on the same trust assumptions as the rest. So you trust the mint to actually give you blind signatures back. But if another user would be an exchange, basically, then you could do it atomically. So you can have this relationship with another user, similar to what I explained as well. But right now, it's only the mint doing it. Yeah. I think that's it. Thank you for your attention.
Thanks, Calle.